Welcome to Activity and the Systematic Treatment of Equilibrium. So first let's talk about ionic strength. So let's examine a saturated solution of calcium sulfate in distilled water. Well, if it's saturated, that means that we have some solid calcium sulfate around, and that means that we have this equilibrium occurring. We have some solid calcium sulfate dissolving into aqueous calcium ions and aqueous sulfate ions. And we know the KSP there is 2.4 times 10 to the minus 5. Now, the solubility of calcium sulfate is 0.015 molar, but not all of it is dissociated. Now, the undissociated ion pair calcium sulfate aqueous has a significant concentration. So that undissociated ion pair has a concentration of 0.005 molar. The calcium ion concentration is 0.010 molar, and then the sulfate concentration is 0.010 molar. So this ion pair is half the concentration of the dissociated calcium ion. Now, if we add a salt containing ions that do not react with either calcium or sulfate and aren't calcium or sulfate themselves, for example, if we add potassium nitrate, the solubility of calcium sulfate increases. Now that seems strange, because if we're looking at this in terms of Le Chatelier's principle, adding some salt that is not part of the reaction, the solubility equation, we're not adding a reactant, we're not adding a product, so Le Chatelier's principle says we shouldn't be shifting the equilibrium one way or the other. But if we add 0.050 molar potassium nitrate, then the concentrations of calcium and sulfate increase by about 30%. So this is a significant effect. Now, this increased solubility effect is seen with most other sparingly soluble salts when an inert salt is added, or a so-called inert salt. Now, why does this happen? Now let's examine one particular calcium ion and one particular sulfate ion in solution. Now the sulfate ion is surrounded by cations, the calcium and potassium ions. And it's also surrounded by some anions, other sulfate ions and nitrate ions. However, the anions are repelled and the cations are attracted to our sulfate ion, and thus there will be more cations than anions in the immediate vicinity of our sulfate ion of interest. Now, this region of imbalanced ionic charge is called the ionic atmosphere of the ion of interest, so around our sulfate ion. Now, the net charge over time of that ionic atmosphere is less than the charge on the ion it surrounds. That is, the magnitude of that charge is lower than the magnitude of the charge on our sulfate ion. So the magnitude of that charge of the ionic atmosphere over time, that net charge over time, is less than 2 because sulfate has a charge of 2 minus. So in the case of our sulfate ion, we have an anion, and then around that anion we have this sort of cloud, this ionic atmosphere that is partially positively charged, with some charge that's less than 2 plus. Around our cations, so around our calcium ions, we would have an ionic atmosphere that is partially negatively charged, with a charge that is less than 2 minus, or closer to neutral than 2 minus. So our calcium ion is likewise surrounded by a negatively charged ionic atmosphere. The ionic atmosphere attenuates the attraction between our calcium ions and our sulfate ions. Now, the greater the ionic strength of a solution, that is, the more ions we have in solution, then the higher the net charge of the ionic atmosphere. And thus, increasing the ionic strength of the solution, putting more ions in solution, decreases the attraction between the cation and the anion. And this then causes the solubility to increase. Because, of course, if we're decreasing the attraction between our cation and anion, then they are less likely to recombine and precipitate out as a solid. So by decreasing that attractive force between the two, we are effectively shifting that equilibrium towards the dissolution process, or away from the precipitation process. So let's define ionic strength. We're going to symbolize it with the Greek letter mu, and it's a measure of the total concentration of ions in solution, with ions weighted by their charge. So an ion that has a charge of 1 plus is weighted less than an ion that has a charge of 2 plus, and so on. So the ionic strength mu is equal to 1/2 times the quantity of C1 times the square of Z1 plus C2 times the square of Z2, and so on, where C is the concentration of the species that we're interested in, so the first species, second species, and so on, and Z is the charge of that species. In other words, the ionic strength is equal to 1/2 of the sum of the concentration times the square of the charge for each species. So now let's turn to activity and activity coefficient. To account for the effect of ionic strength, we replace our concentrations with activities. Now we symbolize activity with a lowercase a, so A sub C is the activity of some species C, and that is equal to the concentration of species C times the activity coefficient of C, which we symbolize with a gamma. So the activity coefficient measures the deviation of behavior from ideality. In other words, it's a correction factor for what the apparent concentration is. That's effectively the activity. The activity of C is essentially the effective concentration of C. So the activity coefficient is then a correction factor for how effective that concentration of C is. If we have a concentration of 1 molar of C, but it actually acts like it's a half molar solution in C, then the activity is 0.5 molar. That means that the activity coefficient, this gamma, is 0.5. Now, this means that we need to update our definition of an equilibrium constant from using concentrations to using activities. So remember, with our generic equilibrium, we had A plus B going to C plus D. That means that now we have our equilibrium constant K is not equal to the product of the concentrations. It's now going to be equal to the products of the activities raised to the coefficients of lowercase a, b, c, d. Now, we can then replace those activities with our concentrations and our activity coefficients. So we have the equilibrium constant K is equal to the concentration of C raised to the C power times the activity coefficient of C raised to the little c power, and so on. Now, if the concentrations of calcium ion and sulfate ion increase with increasing ionic strength, then the activity coefficients must decrease with ionic strength. So at low ionic strength, the activity coefficients approach 1, and this new definition of equilibrium constant approaches our old definition of equilibrium constant. That is, in dilute solutions, the difference between our new equation with activities and the old equation with just the uncorrected concentrations will be approximately the same value. They will approach one another. But at higher concentrations, our old version with just the concentrations will begin to fail, and it will fail more and more so as the ionic strength gets higher, as the concentrations get higher. So note that the values of equilibrium constants collected in tables are often not given for the limit of ionic strength of 0, but instead are the so-called old definition equilibrium constant under certain conditions. Now the conditions then have to be specified in that table. Now we can calculate the activity coefficient using the Debye-Huckel equation. So the Debye-Huckel equation is given here. Log base 10 of our activity coefficient gamma is equal to minus 0.51 times z squared times the square root of mu divided by 1 plus this quantity, alpha times the square root of mu divided by 305, where z here is the charge of the ion, the mu is the ionic strength of our solution, and this alpha here in the denominator is the size in picometers of our ion. So note that this is just an approximation, and it only works well for ionic strengths that are less than or equal to about 0.1 molar. Also note that this ion size that we were measuring in picometers is not the literal size of the ion, but rather the effective size of the ion. That is, it represents the size of the hydrated ion, at least in aqueous solution. So small, highly charged ions have larger effective sizes than large, weakly charged ions because the small, highly charged ion will have more solvent molecules bound tightly to it. It'll have more water molecules around it in aqueous solution. And that means its effective size is much, much larger. So something like a hydrogen ion, which is just a single proton, that has a literal size that's quite small. Remember that a hydrogen ion in water will complex with a large number of water molecules, and thus its effective size is quite large. Whereas a much larger ion has a much smaller effective size because it's unable to complex with nearly as many water molecules. So over here, you can see a graph where on the left side we've got the activity coefficient, and along the bottom we have the ionic strength. So from 0 to 0.1 molar, where 0 is on the left side and 0.1 molar is all the way over here on the right side, then the activity coefficient varies as follows. As the ionic strength increases, so as we move to the right, then gamma, the activity coefficient, decreases. So in all cases here, the activity coefficient is decreasing. Note that the different lines here are for the different charges, where the top charge is plus or minus 1, and then plus or minus 2, and so on down to plus or minus 4 on the bottom one here. Now, as the magnitude of the charge on the ion increases, the departure of gamma, our activity coefficient, from 1 increases. That is, as we get more and more charge, the slope of this curve gets more and more negative. Also, as the ion size increases, the departure of gamma from 1 decreases. That is, as the ion gets larger, its effective size gets smaller, and that means that if we have larger ions, they're going to depart less from ideality. Our activity coefficient is going to remain closer to 1 for longer periods. Now in the book, there's this table showing for various ions and ion sizes and ionic strengths, it gives the activity coefficient. And you can see that for those ions that have a charge of plus or minus 1, you can see a range of sizes. Up here at the very largest effective size, we have the hydrogen ion, and then down at the lower effective ion size, we have much larger ions like ammonium or silver ion, cesium ion. Now for these ions, the activity coefficient at an ionic strength of 0.1 molar is around 0.8. But when we move down here to ions that have a charge of plus or minus 4, we see much lower activity coefficients that are below 0.1. So again, the more highly charged the ion is, the more the activity coefficient will change as the ionic strength increases. Now let's take a moment to discuss the activity coefficients of neutral compounds. So neutral molecules have no ionic atmosphere around them because they have no charge. Now their activity coefficients do not deviate significantly from 1 at ionic strength of 0.1 molar or below. And so we're going to assume that for neutral compounds, gamma equals 1. Now in the case of a gas, we're not going to use the term activity, we're instead going to use the term fugacity, which is defined like this. The fugacity of species C is equal to the partial pressure of species C times gamma of C, which gamma here now is not the activity coefficient, but it's now the fugacity coefficient of species C. So again, the activity coefficient for a gas is called the fugacity coefficient, and that fugacity coefficient is a measure of the deviation from ideal gas behavior for that gas. Now because we normally work at conditions under which gases approximate ideal gases, we will set the activity of gases equal to their pressures in bar. That is, we're going to assume that the fugacity coefficient here is 1, or pretty close. So up until now, we've been talking about ionic strengths that are still relatively low, ionic strengths of 0.1 molar or below. But now let's talk about at higher ionic strength. So at high ionic strength, so this is over 1 molar, then the activity coefficient of most ions increases again. Now this effect is because the solvent is no longer simply water, but a mixture of water and the concentrated ions. Now, from now on, we will assume we are working with dilute aqueous solutions. That is, it's important for you to know that at high ionic strength, we get this effect that occurs. At low ionic strengths, we have our activity coefficient decreases as the ionic strength increases. But when we get to really, really high ionic strength, then that activity coefficient increases and can increase above 1.0. But most of the time, we're not working with solutions that are this concentrated. If you are, you're going to have to modify some of the conclusions that we get to later on in the course. But from now on, we're going to assume that we're working with more dilute solutions, so our concentrations are below 1 molar, and probably below 0.1 molar, or rather, our ionic strength is below 0.1 molar. So now that we know a little bit about activity, let's go back and talk about pH again. So when we measure pH with a pH meter, we are not measuring the negative logarithm of the concentration of the hydrogen ion. We are in fact measuring the negative logarithm of the activity of the hydrogen ion. And thus, a better definition of our pH is not pH equals minus log base 10 of the concentration of hydrogen ion. It's pH equals minus log base 10 of the activity of the hydrogen ion, which we can then write as minus log base 10 of the quantity hydrogen ion concentration times the activity coefficient for hydrogen ion. So let's calculate the pH of pure water at 25 degrees C. We know we've got our autoionization of water. We know that Kw is then equal to the activity of hydrogen ion times the activity of the hydroxide ion, which we can then write as the concentration of hydrogen ion times the activity coefficient for hydrogen ion times the concentration of hydroxide ion times the activity coefficient for the hydroxide ion. And we know that Kw has a value of 1.0 times 10 to the minus 14. Now we know that hydrogen ion and hydroxide ion are produced in a 1-to-1 ratio. That is, their concentrations must be equal, because if we have pure water, then the only source of either one of them is this reaction, the autoionization of water. We don't have any acids or bases around. And that means that we can then call those concentrations X. So the hydrogen ion concentration is equal to the hydroxide ion concentration, which is equal to X. So now, up in this equation, we can then say Kw is equal to X times the activity coefficient of hydrogen ion times X times the activity coefficient of the hydroxide ion. And again, we still know that value is equal to 1.0 times 10 to the minus 14, assuming we're working at 25 degrees C. Now, the ionic strength of pure water is pretty near to zero, because the only ions we have in solution are hydroxide ion and hydrogen ion, and those concentrations are going to be fairly low, around 10 to the minus 7 molar. And that means that we can assume that the activity coefficients are nearly 1, and that means, so now we've replaced a 1 in there for each of our activity coefficients, so now x squared equals 1.0 times 10 to the minus 14, so then x is the square root of 1 times 10 to the minus 14, which is 1.0 times 10 to the minus 7 molar. And now we can go ahead and calculate our pH, which works out to be 7.00. So we haven't really changed anything there. Now, this is an approximation because we've approximated our activity coefficients as 1. So that's a pretty good approximation because the ionic strength is going to be so low. We're so far from that 0.1 molar mark. So this is an okay approximation to make. But instead of pure water, now let's calculate the pH of water that contains 0.1 molar potassium chloride at 25 degrees C. Now, potassium chloride is not an acid or a base. It's neutral, which means that the only sources of hydrogen ion and hydroxide ion are still that autoionization of water. So we can still say the hydrogen ion concentration is equal to the hydroxide ion concentration, which is equal to then X. And we can still write our same equation here for the equilibrium constant, but in this case the ionic strength is 0.1 molar. Now, reading the activity coefficients from the table that we showed earlier, table 7.1, then gives us an activity coefficient for the hydrogen ion of 0.83 and an activity coefficient for the hydroxide ion of 0.76. And when we plug those values in here, now, they're not 1 anymore, so now we're going to have a different pH. So now, when we solve that, we get X is equal to 1.26 times 10 to the minus 7 molar, which is a higher value than what we had before. Remember, before we had 1.0 times 10 to the minus 7 molar. But now the activity of hydrogen ion does not equal the concentration. So when we calculate our pH, again, we have to use the activity there, which is then minus log base 10 of the hydrogen ion concentration times the activity coefficient. So we have our minus log base 10 of 1.26 times 10 to the minus 7 times 0.83, which then gives us 6.98. So note that the pH has changed when we added potassium chloride, but potassium chloride is not an acid or a base. In other words, we've changed the ionic strength of the solution, and that has changed the pH. Now, the pH hasn't changed a whole lot. It's only changed by 0.02, which is probably within the error of your pH meter. So it's not very much. But note that the concentration of hydrogen ion has increased by 26% compared to what it was with pure water. So we haven't changed the pH a whole lot, but we have in fact changed the hydrogen ion concentration by a decent bit. In other words, more water has dissociated, but due to the ionic strength of the solution, most of that increase in concentration has been masked by a decrease in the activity coefficient. So now let's turn to the systematic treatment of equilibrium, how we can solve equilibrium problems in a systematic fashion. So the systematic treatment of equilibrium is a method for dealing with all types of chemical equilibria, regardless of how complex they are. So we often simplify the calculations by applying certain conditions or approximations to them to make our job easier. However, even with simplification, the calculations are usually pretty tedious, and so we often use spreadsheets to solve the calculations numerically instead of analytically or algebraically. That is, if we can get a computer to do the work for us, we can get an answer that's an approximation, but it's really close to the analytical answer, the algebraic answer. And it's a lot easier for us to do that in most cases. So to start, we must write a system of equations to solve the equilibria. Now we must have as many independent equations as we have unknowns. That is, concentrations or activities of chemical species. Now we write one equation for each chemical equilibrium, one for the balance of charge, and one for the balance of mass. Now the charge balance states that the sum of the positive charges in solution must equal the sum of the negative charges in solution. That is, the solution has to be neutrally charged overall. So however many positive charges you have, that must be equal to the number of negative charges that you have. So let's examine a solution containing hydrogen ion, hydroxide ion, potassium ion, dihydrogen phosphate, monohydrogen phosphate, and phosphate ion. So the charge balance is then the positive charges that we have, the concentration of hydrogen ion plus the concentration of potassium ion, and that must be equal to the negative charges that we have, so the hydroxide ion concentration plus the dihydrogen phosphate ion plus 2 times the concentration of monohydrogen phosphate, because we have a charge of 2 minus there, plus 3 times the concentration of phosphate ion, because we have a charge of 3 minus for phosphate. So again, note that each concentration is multiplied by the magnitude of the charge on that ion. And this makes the general form of the charge balance something like this, where we have N1 times the concentration of C1 plus N2 times the concentration of C2, and so on, equals M1 times the concentration of A1 plus M2 times the concentration of A2, and so on, where the concentration C sub I is the concentration of the ith component. The A's there are the concentration of the ith anion. C was the cation, A is the anion. N is the charge on the corresponding cation, and M is the charge on that corresponding anion. So now let's turn to the mass balance. The mass balance states that the mass of all species in a solution containing a particular atom or group of atoms must equal the amount of that atom or group delivered to the solution. That is, a statement of the conservation of mass for that particular element or polyatomic ion. So let's examine a solution prepared by dissolving 0.050 moles of acetic acid in water to give a total volume of 1 liter. Now the acetic acid partially dissociates into acetate and hydrogen ions. We've got our acetic acid dissociating into acetate and hydrogen ions. Now the sum of the acetic acid and the acetate concentrations must be equal to the amount we initially added, which was 0.050 molar. That is, 0.050 molar must be equal to the concentration of acetic acid plus the concentration of acetate. Now let's examine a case where we don't know how much of our species we have added to the solution. So let's say a solution is prepared by dissolving lanthanum iodate in water. We don't know how much dissolves, but we do know that we have this reaction going on. We have the lanthanum iodate solid dissolves to form lanthanum ions and iodate ions. We know that the iodate concentration must be equal to 3 times the lanthanum concentration. Now, if the solution also contains the ion pair where we have 1 lanthanum and 1 iodate bonded, and let's say it also contains the hydrolysis product lanthanum hydroxide, where we have a single hydroxide complex with our lanthanum ion, then the mass balance would be this. Remember, we have our total iodate concentration must be equal to 3 times our total lanthanum concentration, and that means that the iodate concentration plus the concentration of our ion pair must be equal to 3 times the concentration of our lanthanum ion, where it's unbound, plus the concentration of our lanthanum iodate ion pair, plus the concentration of our hydrolysis product. So now our systematic treatment of equilibrium is then given here. So the first step was to write the relevant equations. We did that. The second step is to write the charge balance equation. The third step is to write the mass balance equations. Now note, there may be more than one. The fourth step is to write the equilibrium constant expression for each chemical reaction that we wrote up here in step 1. Bear in mind that this step includes activities, not simply the concentrations. Now the activities can be replaced by the concentrations and the activity coefficients, which we will generally do. The fifth step is then to count the equations and the unknowns. If there are more unknowns than equations, then you must either find additional equilibria or fix some concentrations at known values. Now this may involve making an assumption about the concentration. Later that assumption must be checked once the other concentrations are known to see whether that assumption is in fact valid. The sixth step is then the big one, solve for all unknowns. This is likely the hardest step, provided that you know the relevant equations in step 1. Now in theory, you can solve for n unknowns if you have n equations, although this may be quite tedious. Now in practice, you may wish to use a spreadsheet to solve the equations numerically instead of algebraically. because you can often get close enough to the right answer, close enough being with plenty of sig figs. So to solve the equations numerically, then some concentrations are given somewhat reasonable starting values, and the other concentrations are then calculated. And then the concentrations given the starting values are calculated using the other concentrations that you've calculated, and then that process is repeated with the newly calculated values as the starting concentration. And this is then repeated over and over again. It's iterated until the calculated concentrations no longer change, and this may take a large number of iterations, but computers are very good at this. It usually doesn't take the computer very long to go through those iterative processes. So let's examine some examples to see what we can do by hand and when we need to turn to spreadsheets, when we need to use a computer. So for our first example, let's find the concentrations of species in an aqueous solution containing 0.010 moles of ammonia in 1.000 liters of water. Now, the main equilibrium is the base hydrolysis reaction with ammonia stealing a proton from water to give us ammonium ion and hydroxide ion. Now, the Kb here is equal to 1.76 times 10 to the minus 5 at 25 degrees C. But because we have water around, we also have the autoionization of water occurring. And again, we know Kw equals 1.0 times 10 to the minus 14 at 25 degrees C. This equation, the autoionization of water, you'll be able to write for any set of equilibria in which you have water present as a solvent, which is, in this class, going to be most of them. Now, this means that we need to find the ammonia concentration, we need to find the ammonium concentration, we need to find the hydrogen ion concentration, and the hydroxide ion concentration. Now, we know the relevant equations, so let's write the charge balance. We know our positive charges have to be on one side, our negative charges must be on the other. So we have ammonium ion concentration plus the hydrogen ion concentration must be equal to the hydroxide ion concentration. Note that the ammonia is not present in our charge balance because it's not charged. And now we can write our mass balance. We know that the ammonia concentration plus the ammonium concentration must be equal to 0.0100 molar. And we're going to call that F, where F here is our formal concentration of ammonia. That's how much we put in, the total amount that is in there. And now we can write our equilibrium expression. We have our Kb is equal to the concentration of ammonium times the activity coefficient for ammonium times the hydroxide ion concentration times the activity coefficient for hydroxide ion divided by the ammonia concentration times the activity coefficient for ammonia. Now we know ammonia is not charged, so we can approximate this activity coefficient for ammonia as 1. We know that that value is equal to 1.76 times 10 to the minus 5. And then we have our Kw is equal to the hydrogen ion concentration times the activity coefficient for hydrogen ion times the hydroxide ion concentration times the activity coefficient for hydroxide ion, which is then equal to 1.0 times 10 to the minus 14. And note that this is the only step where the activity coefficients enter the problem. They're not there in the mass balance or the charge balance. So we now have 4 equations and 4 unknowns, and we can now solve the problem. That is, we don't need to make any assumptions here. So here are our 4 equations, and now we can go ahead and solve them. So to solve the problem, first let's ignore the activity coefficients for the time being. We need to eliminate one variable at a time until only one variable remains, until only one unknown is left. So let's start by expressing each concentration in terms of the hydrogen ion concentration. From the autoionization of water, we can always say that the hydroxide ion concentration is equal to Kw divided by the hydrogen ion concentration. And now we can use this in the charge balance equation and then solve for the ammonium concentration. So we replace the hydroxide ion concentration here with our Kw over H plus and then rearrange. So now we have ammonium concentration on one side is equal to Kw over hydrogen ion concentration minus the hydrogen ion concentration. And now we can use that equation in the mass balance to express the ammonia concentration in terms of the hydrogen ion concentration. Remember, we knew that the ammonia concentration plus ammonium must be equal to 0.0100 molar, and that was equal to F, our formal concentration, which means that the ammonia concentration must be equal then to F minus the ammonium concentration. And we can now replace our ammonium concentration. So that gives us the ammonia concentration is equal to F minus Kw over the hydrogen ion concentration minus the hydrogen ion concentration. And now we can replace our ammonia concentration, which we have now in terms of hydrogen ion, our ammonium ion concentration, which we have in terms of hydrogen ion, and the hydroxide ion concentration, which we have in terms of hydrogen ion concentration. We can replace all of those in our Kv expression to get it all in terms of the hydrogen ion concentration, again ignoring our activity coefficients, which then gives us this big guy. Now, in principle, we can solve this equation because we have only one unknown, the hydrogen ion concentration. But it's going to be difficult to do this algebraically by hand. Now, we could instead make a guess as to what the hydrogen ion concentration is and compare the right side to a known value for Kb. Now, your guess is going to be wrong, so you plug in, let's say, a smaller value. If your new result is closer to the value of Kb, then we continue guessing smaller values. If it is not closer, then we guess a bigger value. Now, we could repeat this until we arrive at a value for hydrogen ion concentration that gives a result that's equal to the known value of Kb. We basically solve iteratively. We guess again, see if we've gotten a better guess, and we keep doing this until our guess is equal to the Kb value. Now, this is going to be tedious to do by hand, and a computer can do this much, much faster than we could do so by hand. So Excel has a way of doing this, which we're going to look at a little bit later. Now, remember that we haven't taken activity coefficients into account yet. Now, we could find the concentrations of our ions and then calculate the ionic strength, which we can then use to calculate the activity coefficient. We can then plug these activity coefficients into our equations and solve for the concentrations again, and then we'll need to recalculate the ionic strength using our new concentrations and then recalculate the activity coefficient. We'd have to then repeat this until our concentrations change by a small amount. Now, less than 1% is generally acceptable. Now, this is also pretty darn tedious, and this is a rather simple equilibrium problem. Remember, we only have two equilibria occurring, the autoionization of water, which we're just about always going to have, and one other equilibrium. So instead of going through all of that, let's instead make a simplifying assumption. We know that ammonia is a base, so we can expect the hydrogen ion concentration to be much, much less than the hydroxide ion concentration. For example, if the pH is 9, then the hydrogen ion concentration is 10 to the minus 9 molar, and the hydroxide ion concentration is 10 to the minus 5 molar, which gives us 4 orders of magnitude difference there between our hydrogen ion concentration and hydroxide ion concentration. And there, we've only changed the pH by 2 units. So if we change the pH by 1 unit, then we still have a 100-fold difference in the concentration between hydrogen ion and hydroxide ion. So this ought to be a pretty good assumption. So let's re-examine our Kb expression now using this approximation. Here's our Kb expression that we had with the hydrogen ion concentration in there. Now, if the hydrogen ion concentration is pretty small, that means that this value here is going to be pretty small compared to that value, and that means this value here is also going to be pretty small. So let's cancel those out. Let's ignore those two terms. And that then gives us this. So on the top here, we have our hydroxide ion concentration squared, and then in the denominator, we have our formal concentration minus the hydroxide ion concentration. So now we can solve this using the quadratic formula, and then once the hydroxide ion concentration is known, we can calculate the remainder of our concentration. Now let's look at a second example. Suppose we want to find the concentrations of the major species in a solution that is saturated with calcium sulfate. Well, we know that we have the dissolution process, so solid calcium sulfate dissolves and dissociates into calcium ions and sulfate ions, but we'd also have some solid calcium sulfate that dissolves but does not dissociate, that is, it stays as the ion pair. We'd have some calcium ions that form a complex with hydroxide to form a calcium hydroxide complex, and it then would give off hydrogen ions. We could have sulfate remove a proton from water to become the monohydrogen sulfate, also then giving us some hydroxide ions. And then, of course, we always have our autoionization of water into hydrogen ion and hydroxide ions. And so now we have 5 equilibria. We have 5 values for our equilibrium constants. So now let's write the charge balance. We know we have our cations must be equal to our anions. So 2 times the calcium ion concentration plus the concentration of our calcium hydroxide complex plus the hydrogen ion concentration must be equal to 2 times the sulfate ion concentration plus the concentration of our monohydrogen sulfate plus the concentration of our hydroxide ion. And now we can write the mass balance. We know the total calcium concentration must be equal to the total sulfate concentration. So the concentration of calcium ions plus the concentration of our ion pair calcium sulfate must the concentration of our calcium hydroxide complex must be equal to the concentration of our sulfate ion plus the concentration of our calcium sulfate ion pair plus the concentration of our monohydrogen sulfate. So now we can write the equilibrium expression. So we have KSP equals the calcium ion concentration times the activity of our calcium ion times the sulfate ion concentration times the activity of our sulfate ion, which is equal to 2.4 times 10 to the minus 5. We have the equilibrium constant for our ion pair is equal to the concentration of our calcium sulfate ion pair which is equal to 5.0 times 10 to the minus 3. We have our Ka, which is equal to the concentration of our calcium hydroxide complex times the activity coefficient for our calcium hydroxide complex times the hydrogen ion concentration times the activity of our hydrogen ion concentration divided by our calcium ion concentration times its activity coefficient, and that equals 2.0 times 10 to the minus 13. We've got our Kb, which is equal to the concentration of our monohydrogen sulfate times the activity coefficient for our monohydrogen sulfate times the concentration of our hydroxide times the activity coefficient for our hydroxide divided by the sulfate ion concentration times the activity coefficient for sulfate ion, and that then equals 9.8 times 10 to the minus 13. And then finally we have our Kw equals the hydrogen ion concentration times the activity for hydrogen ion times the hydroxide ion concentration times the activity for the hydroxide ion, which is equal to 1.0 times 10 to the minus 14. So now let's go ahead and count the equations and the unknowns. We have 7 equations, we have 7 unknowns, so we can, in principle, solve this, although it might be pretty tedious. So the next step is to solve. Now, this is not going to be easy, so let's make some simplifying assumptions. Now, the Ka and the Kb are small compared to the Ksp and the K for the ion pair. Now, remember the Ka and Kb are around 10 to the minus 13, the Ksp is 10 to the minus 5, and K for the ion pair is 10 to the minus 3. So the acid-base equilibria are going to be insignificant compared to the latter two, the Ksp and the ion pair. Now, we don't know the activity coefficients, so let's set them all equal to 1. We'll solve for the concentrations, and then we'll calculate the ionic strength and the values for our activity coefficients, and then repeat until the concentrations no longer change. So if we ignore the acid-base reactions, then the autoionization of water is independent of the remaining 2 equilibria, and that means it's easy to find out the concentrations of our hydrogen ion and hydroxide ion because they must be equal to one another. So after applying our assumptions, we now have 2 remaining equilibria. We have our dissolution process with our Ksp, and we have the formation of our ion pair. And that now leaves us with these 4 equations. But note here that the calcium ion concentration in this last equation here cancels. Right? We've got it on the left side, and we have it on the right side. And that now leaves this last equation, which was our mass balance, equal to our third equation, which was our charge balance. Because there, we just have a relationship between our calcium ion concentration and our sulfate ion concentration. If we just divide this third one by 2, then we have what we now have left in our fourth equation, which means we really only have 3 equations. So we now have 3 unknowns, and we have 3 equations. Remember that we've set the activity coefficients equal to 1 temporarily. We'll go back and examine that assumption later. And now we can go ahead and solve. So let's start with our Ksp. We've got Ksp equals the calcium ion concentration times the activity coefficient. Well, we're going to set that as 1. So we've got Ksp equals the calcium ion concentration times the activity coefficient times then the sulfate ion concentration, but we know the sulfate ion concentration is equal to calcium ion concentration, so let's plug that in. And then the activity coefficient for sulfate ion, which we're going to say is 1, and we know that equals 2.4 times 10 to the minus 5. Well, then when we solve that, we just take the square root, and that gives us 4.9 times 10 to the minus 3 molar for our concentration of calcium ion. Now, we know the concentration of sulfate is that same value, 4.9 times 10 to the minus 3 molar, and we know that because we have only one unknown here with our ion pair, you know the concentration of our calcium sulfate ion pair must be equal to 5.0 times 10 to the minus 3. So now we know all of our concentrations. So we can now determine the ionic strength of our solution, and from there we can then determine our activity coefficients from table 7.1. So the ionic strength is equal to 4 times 4.9 times 10 to the minus 3 molar, which is then equal to 0.020 molar. That means the activity coefficient for calcium ion is 0.628, and the activity coefficient for sulfate is 0.606, and now we can use these activity coefficients to calculate the second iteration of our concentration. So instead of assuming we have a value of 1 here and there, we're going to plug in these 2 values. That then gives us a calcium ion concentration of 7.9 times 10 to the minus 3 molar, which has changed a good bit from our 4.9 times 10 to the minus 3 molar that we had in our first iteration. So now if we repeat this process a number of times, as we go from iteration 1 down to iteration 6, then our activity coefficients go from 1 and they slowly decrease, and that means that our concentrations are going to slowly increase, and you can see then our ionic strength slowly increases until down here between these last 2, the ionic strength hasn't changed, at least within the number of sigmas that we're reporting here. So now let's check our assumption. We assume that our calcium hydroxide complex and the monohydrogen sulfate concentrations were negligible compared to the calcium ion concentration and the sulfate ion concentration. Now, we can ignore activity coefficients because we're looking to compare orders of magnitude, not the perfectly accurate result. We just want a ballpark. Is the ratio between the values sufficiently high that we don't need to worry about these smaller concentrations? So let's look at our Ka and our Kb. When we solve the Ka for the calcium hydroxide complex and plug in our values, we then get a concentration of 2.0 times 10 to the minus 8 molar, which is significantly lower than the 9.2 times 10 to the minus 3 molar that we had for the calcium ion concentrate. And when we look at Kb and solve for the monohydrogen sulfate concentration, we get a value of 9 times 10 to the minus 8 molar, which again is significantly lower than the 9.2 times 10 to the minus 3 molar that we had for the sulfate ion concentration. So again, these concentrations are 5 orders of magnitude less than the concentrations for calcium ion and sulfate ion, and that means that our assumption was, in fact, reasonable. Anything beyond 2 orders of magnitude, or including 2 orders of magnitude, is going to be fine, because 2 orders of magnitude would be 1% of the concentration. Now, we also assumed that the hydrogen ion concentration and the hydroxide ion concentration were unaffected by the concentrations of our calcium hydroxide complex and our monohydrogen sulfate. Now, this is not entirely true, as these concentrations are not much smaller than the hydrogen ion or hydroxide ion concentration, but it's close. A more accurate calculation of the pH gives a result of pH equal to 7.06 instead of 7.00, but that's close enough. All right, so we've gone through a couple of examples using the activity coefficients, and as you see, they get a little cumbersome. So after this point, the activity coefficients are going to be neglected unless they're desired to prove a point. So from here on, we're going to go back to essentially our old definition of our equilibrium constants in terms of just the concentration. We're no longer going to be discussing them in terms of activity, but you need to bear in mind, keep in the back of your mind, that that's just an approximation. To get a truly accurate number, you really need to go back to using the activity coefficient. But to get the idea of how to solve these problems, we don't need to include the activity coefficients from here on. So again, you should bear in mind that the results of your calculations are going to be close, but they're going to be incorrect. In other words, they'll be within an order of magnitude, but if you really need a closer answer than that, then you need to go ahead and take the activity coefficients into account. In other words, if this is not good enough, then you need to account for those activity coefficients. In this class, ignoring the activity coefficients, except when explicitly stated, is going to be fine. We want to get close enough in, because I know if you can solve the equilibrium problem without the activity coefficients, you can then go back through, do the additional step or the additional iterations involving finding the ionic strength, finding the activity coefficients, plug them in, go back, recalculate your values. I know you can go ahead and do that, but I don't need to have you do all that extra work. So let's find the concentrations of species in a saturated solution of magnesium hydroxide. And of course, we're going to ignore the activity coefficient. So we have our magnesium hydroxide dissolution process. So magnesium hydroxide dissolves to give us magnesium ions and 2 hydroxide ions. We then have a magnesium hydroxide complex that can also form, where we have magnesium ion and a single hydroxide forming a complex. And we have, of course, our autoionization of water. And we can write our equilibrium constant expressions for each of those. We can now write our charge balance, which is 2 times the magnesium ion concentration plus the magnesium hydroxide complex concentration plus the hydrogen ion concentration. Those must all be equal to the hydroxide ion concentration. Now the mass balance is a little trickier. We have 2 sources of species containing hydroxide ions. We have the magnesium hydroxide dissolution, and we have the water autoionization. And that then gives us the hydroxide ion concentration plus the magnesium hydroxide complex concentration must be equal to 2 times magnesium ion concentration plus the magnesium hydroxide complex concentration plus the hydrogen ion concentration. But this equation is equivalent to the charge balance equation. So we still have 4 equations and 4 unknowns, which means we can solve for our concentration. But first, we can make an approximation. So we made the solution from magnesium hydroxide, so we know it will be basic. It will be an alkaline solution. That is, the hydroxide ion concentration must be larger than the hydrogen ion concentration, and so we can ignore the hydrogen ion concentration here, which then gives us this somewhat more simplified equation down here. So that means that we can ignore the hydrogen ion concentration in our charge balance equation, so we're ignoring this guy here, which then simplifies that a little bit. Now, if we solve for the magnesium hydroxide complex from K1 and then substitute that into the charge balance equation. So here's our K1, solve that for the magnesium hydroxide complex concentration, and then plug that value into our charge balance our simplified charge balance from the last slide. That then gives us what we have down here. So we can now solve this for the magnesium ion concentration. So if we factor out the magnesium ion concentration from the left side, we're then left with 2 plus K1 times the hydroxide ion concentration. And if we then divide both sides by that, we're left with the magnesium ion concentration is equal to the hydroxide ion concentration divided by 2 plus K1 times the hydroxide ion concentration. And we can now substitute this value into the solubility product for the magnesium ion concentration. So we're going to take this stuff, plug it in here, and that then gives us the KSP is equal to the hydroxide ion concentration divided by 2 plus K1 times the hydroxide ion concentration times the square of the hydroxide ion concentration, which gives us the hydroxide ion concentration cubed divided by 2 plus K1 times the hydroxide ion concentration. And note that now we have just a single variable in our KSP. So note here that our equation is a cubic equation that can, at least in principle, be solved algebraically. So if we replace the hydroxide ion concentration with x, we end up getting 0 is equal to x cubed minus K1 times KSP times x minus 2 KSP. So you might notice this is similar to the form of a quadratic equation, only in this case it's a cubic equation because we have x cubed. And just like with a quadratic equation, we have a formula for a cubic equation. We have a cubic formula. So we can go ahead and use the cubic formula. Only it's much, much worse than the quadratic formula. So this whole two-line formula here is the cubic formula. So we could, in principle, solve using this cubic formula. But that's going to be awfully hard. It's just going to be really, really tedious to type this into our calculator. Now, because this is going to be really tedious, let's see if we can use a spreadsheet to do guess and check over multiple iterations. That's probably going to be easier and less time consuming than using the cubic formula. So I can't easily show you here how to go through and do this on a spreadsheet, but the book walks you through it pretty well. In figure 7.7, it gives a little example spreadsheet here, and it tells you what you need to type in each of these cells in order to get the computer to do your calculation for you. You can then have it use what's called a goal seek. You want to set a certain cell. This is cell D4, which is this guy here. You're going to have it set that value to 7.1 times 10 to the minus 12 by changing C4, which is our guess for the hydroxide ion concentration, and it's going to go through and try a bunch of things until it gets to a value that it thinks it's close enough. So I highly recommend going through and following that example in the book. Do this with Excel so that you know how to perform this type of calculation. And you'll see, hopefully, that this isn't too difficult once you get the hang of what it is that you're doing. And you can see that Excel is actually a pretty powerful tool. And once you get a spreadsheet like this, save it. And that way in the future, when you get to future problems, you can just come back and edit that spreadsheet for your new problem and get your value. And that's going to be much, much faster than using the cubic formula. And that was activity and the systematic treatment of equilibrium.